In this video, we will look at an introduction to exponential growth by taking a look at the fish population problem that's presented in the module. So here's the problem. Suppose that every year, the population of a certain breed of fish in a lake grows by about 10%. What are the implications? So I want you to suspend your disbelief for a moment that we can actually have a population growing 10% every year. Of course, at some point, that will not happen any longer. There won't be room. But let's just continue with the problem. We can make adjustments later. First, if there were 100 fish in the lake last year, there would now be how many fish? Well, let's remind ourselves about what we do with the 10%. So a couple of things. One is 10%, 10% meaning 10 out of 100, right? The word percent means out of 100, can be converted to a decimal just simply by dividing 10 by 100. So it's 0.10 or 0.1. We take that number and we just use it as a multiplier to add 10%. So if we take the 100 fish in the lake, we multiply that by 10%, we figure out there's 10 new fish added. So after 1 year, we would start with the 100 fish, right? And then we would add the 10 in, we get 110 total fish. However, if there in part 2 were 1,000 fish in the lake, there would now be how many? Well, it's a secondary problem here. If there was 1,000 fish, we would multiply that by 10%, then we would find that to be 100. So in that case, we'd start with the 1,000 fish, add in the 100, we'd have 1,100 fish. In general, what we're trying to remember is that if we have a percent, this is how we can convert it by dividing by 100, and furthermore, we can use multiplication to figure out an amount. Okay, so let's look further at this problem. In the year 2010, the population was 1,000 fish. And since we start with 1,000 fish, we're going to be using this notation presented in a previous module. We're going to use P0, P sub 0, or P naught, right? That just means our initial or starting population. So when we start time, when no time is expired at all, we have 1,000 fish. Okay? How do we calculate P sub 1? Well, I kind of showed it from above. And we're going to talk about two main ways to do this. Okay, so but in general, let's talk about what we did with a calculation. So we started off with a population of 1,000, right? But then we added in the extra 10%, and the calculation I showed you above was that you take the 1,000 fish and you multiply it by the decimal 0.10, right? And that's the total. So what we had done before above, let me just write it down to remind you. We had the 1,000 fish. Remember that 1,000 times 10% was 100, and we ended up with 1,100 fish from above, or 1,100. But what I want to do for the purposes here is take a look at how we could use factoring to think about a shorter form, or like, in other words, a shortcut for what we're doing. So notice that these terms both have a 1,000 in common, so you could factor that out. Now the first term here, all right, is just really 1,000 times 1, and the second term is 1,000 times 0.10. So factoring the 1,000 out, it looks like that. Okay, now if we were to add the numbers in the parentheses, we can see really that if we could just take the 1,000, we could multiply by 1.10, and we would get the same answer. It would give us the 1,100 fish. So we have something that I'm going to introduce here is this 0.10 is the growth rate, right? The growth rate is 0.10 or 10%. But here, we're going to define this as a growth multiplier. Growth multiplier is a little bit of a faster way to get to the answer. You can just multiply by 1.10 to take you directly to the solution. All right, the growth multiplier will be 1.10. So notice that this could be condensed to a shorter form by factoring there, and we can use that to figure out P sub 2 and P sub 3. Now, P sub 2, by the way, we just take P sub 1, remember, and I'll just write it down here. P sub 1 was 1 year later, there's 1,100 fish, right? P sub 2, we can just take the 1,100 fish and multiply by our growth multiplier, right? We're going to add another 10%. Now, I recommend a scientific calculator, which we don't need yet, but we will eventually. So I'm going to take 1,100 multiplied by that growth multiplier, and we get 1,210 fish. And P3, we can just take the answer from P2, which is 1,210 fish. Again, use my growth multiplier and see what we get. We get 1,331. So in other words, you can just keep using this multiplier to make it more efficient. So what we learn from this is that while 10% is the growth rate, 1.10 is the growth multiplier, and we can quickly use this to calculate the population in later years. You'll see more of this in a future video. But continuing below, let's see, if we were to take these values and take a look at a graph, we can see that it doesn't look quite linear, meaning not quite a straight line. So here in our graph, we have the initial population of 1,000. I've graphed years 1, 2, and 3 that we calculated, but I have calculated year 4 and 5 out. And if you just see, it looks like it ever so slightly is curved downwards in that direction, right? It looks like a slight curve. Well, if you would continue that out for more years, if you look further into the future, in fact, this graph shows out to the 30th year, then you can definitely see that it's not linear, right? It's not a straight line. And so this is a different type of growth that we're studying in this module. And this type of growth is called exponential growth. And it increases faster and faster. This term is used a lot in society when people want to say something is growing very quickly. But to really define what exponential growth is, because some people might call it exponential growth when it's not, it needs to have a growth multiplier, meaning that we're having some quantity multiplied by the same value each time. And that's the fast, sort of efficient way that we can get populations way in the future. Let's talk quickly about how I got this number right here at the 30th year. Well, what I did is I took the 1,000 fish. That was the starting population, right? That was my, what we called P naught. And then I just really multiplied by this multiplier each year 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, all the way to 30. So really I did that 30 times. So a quick way to do that on a calculator is just take and raise 1.10 to the 30th power. Now that's where you for sure need a scientific calculator. If you do, you should be able to type that into left to right. I'm just going to type that in 1,000 times 1.10 raised to the 30th power. And it's, it's not an exact whole number. So I'm going to round off to the nearest whole number. I have 17,449 fish after 30 years. So that's quite a bit of growth. Okay, I hope you've learned more about how this model works, and we're going to look at it more later in the module.